Okay. Cool. So thanks very much. So I'm very much not an early career researcher, having hit the big 4.0 this year. Someone who is my PhD student, Chendi Dana. He's a third year PhD student. Well, he's just finished his third year, going into his fourth year. And this is some research that he published. And the second part is also kind of in press at the moment. So Chendi was actually given a bit of money from the Edinburgh Geological Society to do some work on the Gairloch VMS deposit in northwest Scotland. And Chendi's giving you guys a presentation in January on that research. But as I said, this is focusing very much on the Archean in Western Australia. So Chendi's PhD is all about how we use mineral chemistry to try and find ore bodies. And we're looking at deposit types called VMS deposits. And VMS stands for volcanogenic massive sulphide, which think of it as an ancient equivalent of these black smoker hydrothermal vent systems that form on the seafloor, anywhere from 500 meters to 5 kilometers water depth, where you have ecosystems surviving down here. And these things belch out hot hydrothermal fluids carrying gold, lead, silver, zinc, and copper. So we mine these deposits on land in accreted arcs and ophiolites as oceans close. And we work predominantly with drill core, mostly drill core from Australia. And the deposits themselves form from magmatism within the crust. If you have an ocean basin where you have active volcanism, you have magmas in place at quite shallow levels in the crust. This drives seawater through the crust. The seawater goes to depths, gets hotter, picks up metals from leached volcanic rocks at depths. These metal-rich acidic fluid that's quite hot goes back towards the seafloor, and the mineral deposits form at the seafloor as this hot metal-rich fluid mixes essentially with cold seawater. So these things form either at the seafloor themselves, where you can see them forming as hydrothermal chimneys, or just below the seafloor within the top, 100 meters or so of the rock. Now, the important thing of these deposit types is they're the same age as the host stratigraphy, so they're syngenetic. And in our case, we're looking at deposits anywhere between 2.9 and 2.7 billion years old. And these things form mounds of sulphide minerals, such as pyrite, chalcopyrite, which is copper sulphide, sphalerite, which is zinc sulphide, galena, which is lead sulphide, and they're generally underlain by kind of stringer zones where the hot fluids have basically come through the rock. So you get kind of vein-style mineralization underneath the lenses of massive sulphides that are preserved in the rock record. So these things can form in a wide variety of host rocks. They can form in ophiolites, juvenile volcanic arcs, evolved volcanic arcs, be hosted in basalts, andesites, shales, rhyolites. Doesn't really matter. But generally, when the fluids go through them, you hydrothermally alter and change the existing mineralogy of the volcanic rocks. So you take your original quartz and plagioclase and volcanic glass, and you replace it by minerals such as chlorite, white mica, carbonates, and silica. So they generally have really well-defined alteration profiles around the deposits themselves. And this is going to feed into the work that Chendi did. Now, because we can mine or look for mineral deposits in crust that goes all the way back to the Archean, the deposits themselves could be metamorphosed, and some of them are metamorphosed to quite high grades. Now, generally, most of the deposits we mine in the rock record are metamorphosed to green schist facies metamorphic assemblages or lower metamorphic assemblages, so subgreen schist or prehnite pumpelliite. If you go into amphibolite facies or granulite facies, volcanic rocks, those simple mineral assemblages which you can use to vector in or find ore bodies get overprinted, and you form a wide variety of new minerals such as garnet, biotite, amphibole, cordierite, andalusite, and so on. So the simple picture you have towards the deposit becomes obscured, and you can't use the traditional methods that we'd use if you're walking across the ground doing, say, prospecting. So part of Chendy's project was actually what minerals can we use to actually find ore bodies if you're in amphibolite facies metamorphic rocks in the Archean, or even in granulite facies rocks. So we've looked at a few minerals. We've looked at chlorite, white mica, that we'll talk about today. We've looked at garnet. Now we're starting to look at biotite and amphibole, and all of them you can use their mineral chemistry to try and vector in or find halos around ore deposits that have essentially been cooked up due to metamorphism. Okay, so we're in Western Australia. This is the Yilgarn Craton. It's got some of the oldest rocks in the world, up to 3.4 billion years or so. Most of the rocks we're interested in are in the Eastern Goldfield superterrane. We're a few hours drive east of the world famous Kalgoorlie mining camp, and we're in rocks that are about 2.7 billion years old. So Chendy's dated these with uranium lead methods in zircons. The metamorphic grade down here, so we're down here at the King deposit. This is about 2 million tons, about 3.5% zinc. It's got a little bit of lead, it's got a little bit of gold. It's currently sub-economic, but what we're doing is we're using King as a case study, and we're going to apply those methods elsewhere in the volcanic belt in the company's tenements. So the company, Black Raven Mining, have 445 kilometers of stratigraphy along strike to look for these VMS deposits. So we're taking what we know from the King deposit, and we're going to expand it onto the new exploration targets. I'm going to talk about that in the end. This is just a cross-section through the King deposit, and it's essentially overturned volcanic stratigraphy that's cooked up to amphibolite facies metamorphism, and you essentially have some older mafic rocks in the footwall. You have a biotite muscovite schist and a garnet amphibolite, and then overlying that you have some felsic, dacitic to rhyolitic volcanic rocks, which are now chlorite muscovite quartz schists. There's your massive sulphide horizon in red, and then this in yellow, this is what we call the hanging wall. This formed above the ore deposit after the ore deposit formed at the seafloor. Interestingly, there's this unit through here of very chlorite-rich rocks, and this is, we think, a pathway that the fluids moved through at the time of mineralization. Okay, so I won't go into too much depth with this. This is the typical mineralogy. So you can see here we have a variety of metamorphic minerals. We have lots of biotite, lots of garnet, actinolite, andalusite, amphibolite, cordierite. We have some garnite in there. So it's a really varied mineral assemblage, but what we do have in nearly all of the rocks is chlorite, and in most of the rocks we have muscovite. So the hope is we can potentially use chlorite and muscovite mineral chemistry to say something about vectoring towards mineralization at King and then applying that elsewhere. So one of the methods we've used is shortwave infrared spectroscopy. So this is, you take your rock and you bombard it with light at different wavelengths, and different minerals have different absorption features. So muscovite has one at around 2200 nanometers. Chlorite has one at about 2250 nanometers. There are other ones for quartz, amphibole, carbonates, and so on. But what you can actually do is you can look at these absorption features for specific minerals and the composition of the muscovite has a bearing on the exact position of the absorption feature. So if we look at a rock and it has a lower wavelength absorption feature, we can say that white mica is likely paragonite. If it has a higher wavelength absorption feature, we can say it's phengite. The same thing for chlorite. If it's lower wavelength, it's more magnesium-rich chlorite. If it's higher wavelength, it's more iron-rich. So it's quite a simple method, and it's a very cheap method that mining companies can use at the rig, at the site, to help to improve their drilling campaigns. So again, I'm not going to go through this in too much detail, but what we essentially found was if you're in basaltic rocks, the chlorite composition is generally iron-rich because it's taking up the iron from the basaltic protolith. If you're in dacitic to rhyolitic rocks, you get quite varied chlorite compositions. The different colors reflect the different wavelengths. And this is all to do with the hydrothermal alteration that's occurred prior to the metamorphism. So you can get very magnesium-rich chlorite closer to the VMS deposit and more iron-rich chlorite further away from the VMS deposit in the same protolith, the same dacitic protolith. And in the hanging wall, we tend to get iron-rich compositions. What we did was we coupled this to whole rock geochemical data, and this is a principal component analysis that Chendi did. But simply, in a nutshell, what we found was an association between magnesium-rich chlorite and proximity to zinc, lead, and antimony mineralization towards the top of the system. And deeper in the system, there's an association with iron-rich chlorite, which is generally higher temperature, and copper tellurium mineralization, okay? So we can use the chlorite to tell us something about where we might be in the system. Is it shallower, cooler, hotter, and deeper, okay? We looked at the white mica chemistry, and white mica chemistry is very powerful for VMS exploration because if you're in the hanging wall of the system, i.e. you're above the ore deposit, where there was no alteration before metamorphism because the rocks didn't exist, because remember they form at the seafloor. If you're in the hanging wall, you always get phengitic white mica, okay? If you're in the footwall, you get muscovitic white mica, but as you move towards the VMS in the footwall, you get paragonitic white mica. And this is just substitutions of sodium, potassium, aluminium, and silicon in the structure. But you can detect these things very easily with this shortwave infrared data set. So here's an example. You can take a basaltic rock or a dacitic rock, and you can end up with very similar white mica compositions because this is all to do with the fluids moving through the rock and altering them prior to the metamorphism. So white mica is really powerful for exploration. This is just a 3D view of the data set. So this is the massive sulphide lens dipping. And these colors show muscovitic white mica, paragonitic, and you can see all the red phengitic stuff in the hanging wall, okay? And again, this is just a core scanner. This is the massive sulphides. You see this purple color for the paragonite around the massive sulphides, and then the blue is phengite that formed after the mineralization. Oops, sorry. One other thing we did is we had to verify this because it's all well and good to say, oh, okay, if it's, you know, longer or shorter wavelength, it's different iron-magnesium ratio. But if you're in white mica, there's lots of different substitutions in the chemistry that can affect that wavelength. So what we did was we did electron microprobe analysis on lots and lots of samples to confirm these mineral chemistry. And here you can see the blue is hanging wall data, it's phengite. The stuff down here, this is muscovite, trending to paragonite. Something fell out of the white mica data, which was very interesting, that if you move in towards the ore body is this data in red. If you move towards the ore body, you get an increase in the manganese content of chlorite. So this is really systematic. We've actually seen it in garnet now as well. As you get closer to the ore body, the garnet becomes more manganese rich, so you can use it as a halo for exploration. If you look at the chlorite, you can see increases in fluorine contents in chlorite as you approach massive sulphide mineralization. And then it's really low in the hanging wall because the rocks weren't there at the time of mineralization. You see it in the white mica as well in terms of fluorine, and it's not on the screen, but we've seen it now in biotite as well. So several minerals which are consistent in terms of actually finding ore deposits. So just to finish up for the last couple of minutes, I just want to show you how we've applied this to a new case study further along strike from the King deposit. So here's the King deposit down here right in the south. This is called King North. This is another prospect they're drilling. This is called Danny's or EBO4. This is the northern area. But you can see there's a lot of stratigraphy to try and find a deposit. Now at King, we have a lot of diamond drill core. So we have really nice core of the rock. We can do logging, do electron microprobe, make nice thin sections. Elsewhere along strike, all we have to deal with is reverse circulation drilling. And what you get from this is piles and piles of rock chips. It's quite good for a PhD student. You can get them to sieve through the dust and find some nice chunks of rock to make thin sections from, to then do more kind of microprobe work. So we're looking at this one called EBO4 in here, also known as Danny's, where there was a sniff of some mineralization there based on a couple of reverse circulation drill holes. So the company put 2 drill holes into it, and like I say, the stratigraphy, all you have to go on are tiny little rock chips surrounded by dust. So for every meter, you get a little pile of dust with a few rock chips in it. And the stratigraphy they had was you had a little bit of mafic in here, but then a huge amount of felsic volcanic rock. Interestingly, you have a lot more magnesium-altered felsic. So this is already looking more prospective than King for mineralization. There were some sniffs of mineralization in the drilling, but then the company thought they'd actually tested the ore horizon because they got quite a high zinc grade in one of their piles of rock dust, okay? Then they hit a big late Proterozoic dike of dolerite, so they ended the hole because they couldn't get through it, and they thought, okay, the target's, there's a bit of zinc, it's kind of dead. So what we did is we looked at some samples through these drill holes, and what we found was this horizon, which they thought was the equivalent to the ore horizon, is still very much in the footwall stratigraphy. Okay, the white mica is still very fluorine rich. In fact, it's more fluorine rich than the stuff at King. The garnet is very manganese rich. Again, it's indicating you're still in the footwall. You've not gone into those hanging wall rocks. And importantly, the white mica is still muscovitic. It's not phengite that you'd expect if you'd gone through the ore horizon into the overlying rocks. So what this means is their cross-section is completely wrong. They haven't tested the ore horizon. The ore horizon is at depth underneath this Proterozoic dolerite dike. So Chendy's work has shown that this really needs a diamond hole to test this properly. And the geochemistry is pointing that this is more prospective than the King deposit. So yeah. So just to conclude, Chendy's work has looked at chlorite and white mica chemistry. He's found some nice halos towards mineralization, both using fluorine, manganese, but also the major element composition of white mica. And despite the metamorphism, you're able to see through it up to amphibolite grade. We're working on a separate deposit called Wheatley, where we're looking at granulite facies metamorphism and minerals such as biotite and amphibole to see if we can see through that as well. So there's Chendy. Like I say, he'll be giving a talk in January, and this is his paper in Mineralium Depositor early this year, and his EMPA data set and his garnet data set is in press in Econ Geol. That should come out in January as well. So thanks very much.